Good morning. Let's see, it's Monday. What did I do this morning? I posted a homework assignment for projectile motion, and I think that's about all I got on there. And also, let's see, an announcement about a test next Monday. And what else? Oh, there's also a practice homework assignment or a practice assignment up there for review for test 1. And that's actually extra credit. So, but the regular homework assignment is not extra credit, it's regular stuff. So we can dive in. We've gotten our feet wet a little bit with projectile motion things, and now we can continue on with that stuff. And here's a problem. Let's see, just for review real quick, I'll consider our things. Projectile motion is when we have a downward acceleration. So the acceleration's downward and its magnitude is 9.81 meters per second squared. And then the projectile is often launched at some kind of an angle, but we have to consider both X and Y motion on this. But it turns out we can split the two apart. And in the X direction, we can write an equation that X is just going to equal X naught plus the initial velocity in the X direction times T. There's no acceleration in the X direction because it's going to point sideways here. And for nearly all of our projectile motion problems, we'll have Y being positive upwards. So we'll have that. V sub x is just equal to whatever it started off as. It's going to be constant. And so in the X direction, things are particularly simple. So that's kind of nice. But the Y direction is more complicated. So we'll have things like in the Y direction, we'll have V sub Y is going to equal V naught Y minus GT. So whatever it started off with, we've got this constant acceleration in the Y direction, and it's downward with that magnitude. Little g stands for 9.81 meters per second squared. Whether it's down or a negative sign or not, if acceleration is downward and that's the negative direction, then we put a minus sign on there. We can also have y is equal to y naught plus v naught yt minus 1/2 gt squared. X naught and y naught are the initial position. If we're clever, a lot of times we'll say that those are equal to 0, but not always. Sometimes we may choose to make the initial position, like if it's 100 feet off the ground or something, or like the first problem we're going to do today. If it's a long ways above, or if it's above where it's going to end up, we may let the point where it ends up be where y is equal to 0, and then the initial position, if it's a ways up, will be something other than 0. So we have that. And whenever you have constant acceleration, you can also sometimes use this equation, which should be, in this case, v sub y squared is v naught y squared minus 2g delta y. Or that might be, instead of delta y, it might be y minus y naught in there. So either delta y or that, they kind of mean the same thing. So that's just a little review of the projectile motion equations, and those are, I think, as they're written in the book. So if you're studying out of there and reading their examples, they'll be using those. So this first problem here, seems crazy. A girl throws a ball horizontally from the top of a 60.0 meter building. That doesn't seem so crazy. Sounds like fun to me. And the ball lands 100 meters from the base of the building. Ignore air resistance. How long is the ball in the air? This sounds like one of those crazy logic questions you see every once in a while where, oh, I don't know. You're on the island of knights and knaves and you talk to a guy with a red hat and you're supposed to figure out, is he a knight or a knave from the fact that he's wearing a red hat? And they really can be figured out, and this can be figured out. And there are some keys in here that will let us do it. One, the ball is thrown horizontally, okay? That means initially it has no y velocity. That means v naught y is equal to 0. Now, it's thrown from the top of a 60-meter building. So if we make a little sketch over here, and 60.0 meters, that's where the ball's thrown from, and it's thrown horizontally, so it's going to come down like this. But y naught, we can say y is 0 at the ground, but that makes y naught equal to 60.0 meters. Now it lands 100 meters from the building, so I don't have a very good scale model here, but that's where it lands anyway, 100.0 meters. That's in the x direction though. Here's what I know in the y direction. I know v naught y is 0. I know y naught is 60 meters. And I know at the end it's going to be down there on the ground. And so from that, can I figure out how long it's in the air? Yes, I can. Turns out this ball will be in the air exactly as long as a ball that you just take to the edge of the building and drop. It's kind of like that situation. If we were in the classroom, I would track down the YouTube video that they did on Mythbusters where they tested that. There was some building down on the San Francisco Bay that's really long, and they were able to go in there, fire a bullet horizontally, and they hooked it up electronically so that at the same instant it was fired, a bullet would be dropped just vertically by this contraption they built, and they showed that they both hit the ground at the same time. So that's a common question that you'll see. In fact, it may be on your homework, I don't know, but that's the idea. So if all I do is consider the y equation for position as a function of time, I can say this: y is equal to y naught plus v naught y t minus 1/2 gt squared. Well, when the ball hits the ground, its y value is going to be 0. Okay. V naught y is 0, so this whole term is 0, and y naught is 60 meters. So here's this equation translated into when the ball hits the ground. I would have 0 is equal to 60.0 meters minus 1/2 times 9.81 meters per second squared times t squared. Okay, now the only thing I don't know in this equation is t. That's my only variable. So if I bring this term to the other side, I'll have 1/2 times 9.81 meters per second squared times t squared is equal to 60.0 meters. Multiply both sides by 2, and I'll get 9.81 meters per second squared times t squared is equal to 2 times 60 is 120, let's see, 120 meters. Actually, if I just add, I can actually keep another significant figure on here. That 2 is exact. And so that's that. And t squared will equal that thing divided by 9.81 meters per second squared. And t will equal the square root of that whole thing. So I'm just going to plug that square root into my calculator. The square root of 120 divided by 9.81, unit-wise, it's going to come out seconds. Because if I divide meters by meters per second squared, flip this and multiply, and I'll have meters times seconds squared over meters, and the meters go away, and I just have seconds squared, but when I take a square root, I get seconds. Then I get about 3.50 seconds. Okay, and that's as many significant figures as I can keep on here. So we just figured out the ball is in the air for 3.50 seconds. Just from that description, we were able to work that out. Now, what must have been the initial horizontal component of the velocity? How could we possibly figure that out? Well, here's the thing. We know how long it's in the air, and we know that in that time it travels 100 meters sideways. And so we can figure out the horizontal, the average velocity in the x direction, but the velocity in the x direction does not change in projectile motion. And so v sub x, which is constant, while it's in the air at least, is just going to equal delta x over t. The t is the 3.50 seconds, so 100.0 meters divided by 3.50 seconds. And I get 28.6 meters per second. Okay, which is a little bit more than 60 miles an hour. Okay, so maybe this girl is a softball player or something like that, where she's used to throwing somewhat fast. If she was a softball pitcher, she could throw quite a bit faster than that, but that's a reasonable value. Then it asks, what is the vertical component of the velocity just before the ball hits the ground? Okay, well, we know it's going to be down, so it'll be negative. The equation that describes my velocity in the vertical direction is v naught y minus gt. So v sub y will equal v naught y minus gt, but v naught y is 0. So this is just going to be minus 9.81 meters per second squared times 3.50 seconds. So, and I'll show you in a second another way to get that. Minus 34.3 meters per second. When you multiply meters per second squared times seconds, this second divides with one of those seconds and leaving me meters per second. The other way I could have gotten that last result was to use that equation that does not involve time. There's one shortcoming of that equation, and I'll show it to you here. v squared equals v sub y squared equals v naught y squared minus 2g times y minus y naught. Okay, and if I look at this, let's see, v naught y is 0. So v sub y squared is going to be minus 2 times g times y naught was 60.0 meters. Y is going to be 0 when it hits the ground. So it'll be 0 minus 60.0 meters. And this all ends up being 2 times g times 60.0 meters. So I know g, and so this is going to be something. But here's the thing. This tells me v sub y squared. It does not tell me the sign of v sub y, except I know what the sign's going to be. You threw it off the building and it's accelerating downward. But this would give me the magnitude of v sub y. And that's one somewhat shortcoming of this thing. You may not always know the sign of the velocity, though, and so this equation will not tell you what that happens to be. So we get that. But anyway, if I plug and chug on here, I could think of this as the absolute value of the velocity in the y direction, and I'd have the square root of 2 times 9.81 meters per second squared times 60.0 meters. When I multiply meters per second squared, remember, even though we have kind of a slash there, that actually represents this. And I'm multiplying that by meters, which you can think of as meters divided by 1 if you want. Multiply the numerators, multiply the denominators, or if you're just multiplying a fraction by anything, that anything multiplies only the numerator. So I'll have meters squared per second squared, but that's under a square root. And when I take the square root, I'll get meters per second. And let's see what I get. That's it. I get 34.3 meters per second. So it worked. I got the same value that I did doing it the other way. And so that's another alternative. If you'd just been asked for the vertical component of the velocity just before it hits the ground, you could do that without figuring out the time in the meantime, or figuring out the time on the way. Okay, then it says, what is the velocity, including both the horizontal and vertical components of the ball just before it hits the ground? Well, one way of writing that is to say v with an arrow is going to have components. It's going to equal the x component of the velocity, 28.6 meters per second, in the x hat direction, and then that y component minus 34.3 meters per second in the y direction. And these hats represent vectors that just have a magnitude of 1, and the only property of this vector is it points in the positive x direction. The only property of this vector is it points in the positive y direction, but multiplying it by a minus sign reverses the direction. So those are the horizontal and vertical components of the ball just before it hits the ground. Sometimes we'll word it when the ball hits the ground, and people will take that to mean, students will look at that and think, oh, after it hits, what's it going to be doing? And what I try to word it just before it hits the ground. So this would be when it's on its way down and it's this far above the ground. What will its velocity be? So that's virtually at the instant it hits the ground. Okay. Some future scientists make a potato gun and manage to launch a potato with an initial velocity of 48.5 meters per second at an angle of 32.2 degrees with the surface. Assume the projectile lands at the same elevation from which it was launched. Okay. Potato guns are things that can be made out of PVC pipe, and you get a PVC pipe with a big enough diameter so a potato fits in there. Well, it mostly blocks the air when it comes out of there. And what you fire the potato with is a lot of times lighter fluid, and it'll be vaporized lighter fluid. And it's quite explosive when you do that. But because it's quite explosive, these things sometimes cause accidents. If the explosion is powerful enough to blow out the plastic, then the people who set off the explosion can be injured by it. So anyway, use under adult supervision. And adult doesn't necessarily mean your 22-year-old uncle or something like that. Anyway, they could be used. Assume it lands at the same elevation from which it was launched. How or what is the maximum height reached by the projectile? Okay, this is more of a typical projectile motion problem, and I'll just make a little sketch of the launching here. And so there's the ground level and that it's launched from. And just draw an arrow that represents the initial velocity. And I don't try very hard at all to get the angle correctly here. I drew an angle bigger than 32.2 degrees, I know for sure, but that's okay. I'll just say this is theta, and theta is equal to 32.2 degrees. And I just do that. So if I wanted to, I could draw myself a little triangle down here that has, move this over, it's got V naught in it, and V naught is made of V naught X and V naught Y. Okay, and this is theta. And there is a nice right triangle. X and Y are perpendicular to each other. So that means V naught X over V naught is the cosine of theta, or V naught X will equal V naught cosine theta. And V naught is that 48.5 meters per second. And this is theta. And so I can just plug those into my calculator. 48.5 meters per second cosine of 32.2 degrees. By the way, when we use a trig function and we're given an angle to so many degrees, we just assume on the trig functions that we will get the same number of significant figures out of there that we put into it. And so, and we're not gonna, you can go crazy worrying about some of this stuff, but that's how we'll work it. So 48.5 times cosine of 32.2, and I get 41.0 meters per second. Now, this is kind of preliminary work that I do on a lot of projectile motion problems, is figuring out V naught X and V naught Y. And I'm sort of looking ahead here. It says, what's the maximum height reached by the projectile? How long is the projectile in the air? And how far from the launch point does it land? That's moved sideways. And so this is, I'm going to need to know this for that last part. So I'll figure it out at the start. But I'll also need V naught Y. And V naught y in this triangle, well, it's this opposite side. This opposite side divided by the hypotenuse is the sine of that angle. And that means that V naught y will equal V naught sine theta. But I think I've got that on your formula sheet just the way it is. Where is it? Maybe I do. Maybe I don't. Oh, projectile motion. Okay. The projectile motion continues over to here. Oh, how about that? No, this is the projectile motion stuff. Okay, wrong box. This is just the free fall. This is the projectile motion box. So at the very top, I give you those V naught x and V naught y formulas. So, but they're based on the right angle trigonometry. V naught sine theta. Okay. 48.5 meters per second times the sine of 32.2 degrees, and that'll just equal something else. 25.8 meters per second. Okay, so that's close enough on those things. Well, I can only keep 3 significant figures. Now, first question asks, what is the maximum height reached by the projectile? Well, here's one way to get it. I can figure out how long it gets to the high point using the equation for the velocity in the y direction, which is v sub y equals v naught y minus gt. What does it do at the very top? It stops going up, and the instant after that, it begins coming down. V sub y is 0 at the high point. And so if I set this equal to 0 and solve for the time, I know v naught y and I know g. I can figure out how long it takes to get to the high point. So now, this is on the way to trying to figure out how high that high point is. How high that high point is, I get because y is equal to y naught plus v naught yt minus 1/2 gt squared. If I know the time to reach that high point, which I can figure out from here, I can plug that into this equation. Y naught, I'm going to let be 0. Let the launch point be 0 in both x and y. So little note to self here, y naught is equal to 0. Okay. So that's one way that I can do that, figure out the maximum height reached by the projectile. If I continue on with this equation and I've got that set equal to 0, I can say that v naught y is equal to gt, or the time to the high point is going to equal v naught y over g. And plug in the numbers. Now, this time is the time from the launch to the high point. And I need to remind myself of that. So let's see, what was v naught y? It was 25.8 meters per second. Divided by 9.81 meters per second squared. So looks like a little over 2.5 seconds. And the way I got that is to just imagine, okay, that's about 25. This is about 10. 25 divided by 10 is about 2.5. So if I don't get that on my calculator, something about a little over 2.5, then I know I punched something in wrong. And it's a good idea to make estimates first. And I didn't get that because I got 2.6 or 0.263 but then I looked and I accidentally only put in 2.58 for the height. So there's a mistake. Okay, now it's one I know how to fix easy. I'll just multiply this by 10 or punch the numbers back in. 25.8 divided by 9.81, and I should get 2.63 seconds. I did. Okay, so now that's how long it takes to get to the high point. This equation will tell me how high that high point happens to be. So that's the way to do it. And I think that's what it is. Yeah, maximum height reached by the projectile. So y will equal y naught, which is 0, plus v naught y, which is 25.8 meters per second, times that time I just figured out, 2.63 seconds, minus 1/2 times g, 9.81 meters per second squared, times that time again, but this time the time gets squared, 2.63 seconds squared. And just plug that into my calculator. I can figure out y max. And then I'll show you another way to do this. So 25.8 times 2.63 minus 0.5 for the 1/2 times 9.81 times 2.63 squared. And I get 33.9. Now, when I multiply these things, a meter per second times a second, the seconds divide out and I'll have meters. Here I've got meters per second squared, but I'm multiplying by seconds squared, and I'll end up with meters again. And that has to be the case. When you're adding or subtracting things, they must have identical units. So that's what I get. Now, here's the other way that you could have done that. And maybe it's less work, maybe it's more, but you would go do this. V sub y squared equals v naught y squared minus 2 times g times y minus y. Excuse me. Y minus y naught. Okay, well, let's see. V sub y is 0 at the top, so this is 0. Y naught is 0. That's 0. Y is what we're after. What's the value of that at the top? I know V naught y, it was 25.8 meters per second. So let's see what this gives us. If I kick these terms across, I get 2gy equals V naught y squared, or y at the top will equal V naught y squared over 2g. Let's see if it works. 25.8 meters per second. And I square that. And then 2 times 9.81 meters per second squared. Got to make sure my units come out. When I square this on top, I'm going to have meters squared per second squared. On the bottom, I've got, hope that's still showing. Yeah, it is. I'll have meters per second squared. Flip this and multiply, and it'll come up here as seconds squared over meters. The seconds squared divide out, and I'll have meters squared over meters, which is just plain old meters. That's good. That's what we're measuring y in. So let's see. Trying to do this in my head. I'm going to have 600 and something divided by about 20. I'll expect a number somewhat bigger than 30. hey, like maybe that one. We'll see. Oops, clear. 25.8 x squared. I knew it was going to be 600 and something because 25 squared is 625. If you have 25 quarters, they're worth $6.25. And I think that's how many are in a roll of quarters, but I'm not sure. Anyway, need to make sure I wrap my denominator in parentheses here. So 2 times 9.81, finish off the parentheses, and I get 33.9 again. So a second way to get y, just in case. And if you kind of look for second ways to do things, it's good practice, gives you lots of practice with these equations. Okay, then it asks, how long is the projectile in the air? Okay, now here's the thing. It's beginning and ending at ground level. So this projectile is following a path that goes like this, where it ends up at the same height that it started from. And when that's the case, it will spend exactly as much time on the way down as it did on the way up. And I can show you that. Let's see, I don't want to get a clean piece of paper to do some more work on here. This will be for B. Got to be careful with this. It's only good when the thing begins and ends at the same point. But let's take a look at our equations for this thing. Here, we figured out the time to the high point. And it was V naught y divided by g. Okay. Now, it's at that high point. The high point, we figured out here, it's V naught y squared over 2g. Here's a way of solving an equation without having to solve a quadratic formula, although this quadratic formula turns out we could solve without using the quadratic formula. But the high point was y equals V naught y squared over 2g. Okay, and I'm just going to leave these in letters. Time from high point to ground. Okay, well, for this part of the problem, I'll put a subscript of h on this y. That's y at the high point. And I'll write down my equation for y as a function of t. Y is equal to y naught, which in our case is y at the high point, plus v naught y t minus 1/2 gt squared. But this v naught y is going to represent that the y velocity at the high point. This is 0 because that's where it stops going up and hasn't started to come down yet. And this y will equal 0 because I want to know how long it takes to get back to the ground. So y at the high point was v naught y squared over 2g. So I'll have 0 equals v naught y squared over 2g minus 1/2 gt squared. And let's see, if I kick that across, I get 1/2 gt squared is equal to v naught y squared over 2g, and divide both sides by, or multiply both sides by 2, because I've got a 1/2 on each side, and I'll get t squared, gt squared equals v naught y squared over g. Divide both sides by g, and I get t squared equals v naught y squared over g squared, and take the square root, and I get t is v naught y over g. Now, this is how long it spins on the way down. That was how much it spent on the way up. They're exactly the same. And so the time of flight is equal to the sum of those two. V naught y over g plus v naught y over g. There's a symmetry to the motion. When you don't have air resistance and you begin and end at the same height, it spends exactly as much time on the way up as it does on the way down. And so the time of flight ends up being 2 v naught y over g. So that's nice to know, but that only works when it begins and ends at the same height. So you have to be a little careful there. That's how long the projectile is in the air. How far from the launch point does it land? Well, now that we know that, I think we figured out what that time was. That was 2.63 seconds on the way up. Twice that is going to be 5.26 seconds. Check that, but 2.63 times 2, yeah, 5.26 seconds. So for part C now, we can bring in our x equation finally. When they say how far from the launch point, that's the distance in the x direction. So x is equal to x naught plus v naught x times t, or you can say x minus x naught. That's how far it travels horizontally. And turns out for this part, you can say x naught is 0, or you don't even have to, but it'll equal v naught x times t. V naught x we'd already figured out. It's 41.0 meters per second. And the t, we just figured out it was 5.26 seconds. And so what do we end up with for this? A lot. It's about 216 meters, which is 2 football fields away. And if these kids launched that potato and they noticed after launching it, hey, there's a bunch of people over there where it might land. If they yelled, people 216 meters away might not be able to hear them. And so what are they going to say? Watch out? What are those people supposed to watch out for? All right. Okay, that projectile motion problem had about everything in it that a projectile motion problem might have. So lots of different things. Let's see what else we could do. Here's one similar to it. A punter kicks a football with an initial velocity of 22.6 meters per second at an angle of 47.2 degrees with the horizontal. Hey, that looks like V naught to me. Initial velocity. Angle of 47.2, that's the launch angle that we've been calling theta. So it's only good at the instant of launch, but that's okay. Okay, leaves the punter's foot 1.47 meters off the ground it's caught by the return man at the same height from which the ball was kicked. So I could call this y naught if I want to, but turns out y final is also equal to that thing. Okay, then it asks, how long is the punt in the air? And then how far is it from where the punt is kicked to where it's caught? Well, what do we know about that time to the high point? Here's what we know. V sub y is equal to V naught y minus gt. V sub y is 0 at the instant, or excuse me, yeah, V sub y is 0 at the instant that it's at the top. And if we figure out that time, we get the time to the high point. But if it's launched and lands at the same height, which this does, because it says same height, it's caught by the return man at the same height from which it was kicked. Okay. Then we've got this mirror image where it spends exactly as much time on the way up as it does on the way down. And we can do that to figure it out, but then I'll show you another way that we can use here. Anyway, V naught y is going to equal V naught sine theta. And I could get a number for it, but I may just wait and calculate it when I need it. So time to high point is, I figured that out from 0 equals V naught y minus gt. And let's see, when I solve that, I get that t is equal to V naught y over g. Time of flight is twice that long. It spends as much time on the way down as it does on the way up. And so that's the time on the way up. Time of flight, I can call that T sub f, is equal to 2 V naught y over g. So that's the time of flight. And how can I answer question B from that? Well, that's how far. That's the x direction. X is equal to x naught plus V naught xt. You can call x naught 0 in this problem if you want to. That's where the punt is kicked from, and then x would be to where it's caught. So if I just do that, put a 0 in there, for that, I will get, this ends up being V naught x times t, but t is 2 V naught y over g. So the range of a projectile, when it begins and ends at the same height, ends up equaling x is going to be, if I reorder this stuff I multiply together, it'll be 2 V naught x V naught y over g. That's the range of a projectile if it begins and ends at the same point. Let me show you another way to get the time of flight. And this is kind of interesting. We start with our y equation. Y is equal to y naught plus V naught yt minus 1/2 gt squared. Okay, now if it begins and ends at the same height, then this y is going to equal y naught. And so I can say at the end, it's got a height of y naught, because for this thing, it begins and ends at the same height. The guy catches it that far off the ground. So y naught is going to equal y naught plus v naught yt minus 1/2 gt squared. Okay. This equation will tell me when the ball is at a height of y naught. Okay, well, since I've got y naughts on each side, I can subtract those away, and I get 0 equals v naught yt minus 1/2 gt squared. I'm solving for time. This is a quadratic equation of sorts, but since t is in every term, I can factor the t out, and I will get 0 is equal to t times v naught y minus 1/2 gt. And imagine if you multiplied this t back through, would it reproduce that? Well, t times v naught y will give you v naught yt. T times minus 1/2 gt squared will give you minus 1/2, or 1/2 gt will give you minus 1/2 gt squared. So when you have two numbers multiplied together that equal 0, this is something you learned in factoring in algebra class, then either this is 0 or this is 0. So one of the answers I get here is t equals 0. Well, that makes sense. Yes, the ball had a height of y naught at t equals 0, because that's the definition of y naught. It's the height of the ball at time 0. So that worked. The other one gives me v naught y minus 1/2 gt equals 0. And kick that across. V naught y equals 1/2 gt. Multiply both sides by 2. You get 2 v naught y equals gt. Divide by g. And you get t is equal to, this is the time of flight now, 2 v naught y over g. Hey, we knew that from before. Okay, but that's another way to get it. So that shows up there. Okay, finally, how far is it from where the punt is kicked to where it's caught? Well, we figured out an equation for that. Let's just stick this in here and see how far the ball goes. We could figure out the time, but this way works too. So, and we haven't done one this way yet. So I would have 2 times v naught, v naught x is v naught cosine theta, v naught y is v naught sine theta, and then I divide by g. And if I look at that thing, I've got v naughts showing up twice. So x is equal to 2 v naught squared cos theta sine theta divided by g. And that's as far as I'm going to go. Some of you who have taken Math 142, which is our trigonometry class, or if you took it in high school, you may remember that 2 cosine theta sine theta happens to be a trigonometry identity, but I don't expect you to learn those things in here, or to remember them for that matter. So I'm just going to punch in the numbers. On 2 times v naught was 22.6, and that gets squared, times cosine theta, cosine of 47.2, in parentheses, sine theta, also, where is it? There it is, 47.2. And I just divide by g, 9.81. How far does it go? It looks like 51.9 meters. That's a pretty good punt, actually. Also, just curious, what's the hang time? That's something, one of those statistics that they like to spout on television when they don't have anything else to say. So 2 times v naught y, and v naught y was wherever it went, v naught sine theta over g. So if I figure out the time that it's in the air, I get a time of 3.38 seconds. And that's how long it's in the air for. 51 meters down there. You better hope some of your coverage guys started running the instant the ball was snapped, and so they get a little bit of a head start on here. Otherwise, the punt return guy will have a few seconds to catch the ball, look around, and decide the best way to run, and that's when they're dangerous. You want to have coverage people down there just about as soon as they're going to be catching the ball. Okay, we're about out at, we're overtime today. Tomorrow we'll do a couple more projectile motion problems. I may make some up. This one lands at the same elevation again. Maybe we've done enough of those. You might just try this one on your own and see how you can do. This problem is in there. This is a snowball rolling off a roof, and is it going to hit the guy or not? So that could be exciting, but we'll do a couple more tomorrow, and then before the test, we'll do some stuff with addition of velocities, but not a whole lot. Okay, any questions on those? Hopefully you're reaching the point on doing those and have done some extra work where you can look at those and have a pretty good idea of where I'm going to go in solving it now. So, but do lots of homework. By the way, on the test, the way it's going to work, and I'll post some stuff about this, I want you to print off some worksheets, and at the top of each worksheet it's just going to say your name, a blank to put your name on, and then problem number, and write, you know, if you're working on problem 1 and so forth. And those will be what you do your work on. You can look at your computer screen to see what the problems actually are. Well, I want you to have your cell phones on Zoom monitoring you while you take the test. So off to the side and a little behind you so they can be looking at your work surface. And that's what you'll do. And when you're done with your test, what you'll do is take those worksheets that you carefully completed and take pictures with your camera of them and convert them into PDFs. So you want to be, you would open something like Office Lens. Office Lens happens to be a free application, and you can have it on both Androids and iPhones. And you'll be able to do that and then submit that as your work. On your test, the work, if a test question is 5 points, say, the work that you show is worth 4 out of 5. The correct answer is worth 1 point. And if somebody does everything right and then accidentally hits a wrong number on their calculator at the end, I'm not going to give them a 0 for the question because the work you set up was correct. So that's something to have in mind. And so show lots of work. Every time you start a problem, write down the equations you're going to use in variable form first, and then start working on solving the problem. And so if I see that you've written down the correct equations, those that apply to the problem, then you'll get something for that. You may not get a lot, but then if you, the more work that you show on the way through the thing, the better off you'll be. So basically, model your solutions on the way I've been doing them, and try to get in the habit of doing that whenever you solve a problem. Okay, I'll turn you loose and I'm going to run out to school this afternoon and gather data for your lab. And I
Oh,
thought
so we're using Zoom to monitor us through our phones then?
right, yep.
Oh, yeah.
Oh, and one thing that you want to do is have your phone plugged in when you're doing that, because using Zoom continually when you're during taking the test will drain your phone's battery. And so you don't want to have your phone be dead when you finish the test and you're trying to send me your test work on your phone. So yeah, I need to keep reminding people of that, because we discovered that fall quarter that running a Zoom meeting on your phone for 70 minutes or so will drain the battery on your phone if it isn't completely charged at the start, but it's better to have it charged all the way through there.
So the
Anyway,
questions we're doing will be pretty similar to what we're doing like here, pretty much. All
yeah,
right.
yeah, and what we've done. And you can't put a ton of them on a test, like, generally 6 or 7 questions on a test are plenty. I usually have some that'll be a few parts, like some of the problems we've been doing here, but not all of them. And there will also be some conceptual questions on there too that are just verbal answers. But and we'll have a review session on probably Thursday at class time, and I'll put out a Zoom, or not a Zoom, a doodle poll to see some other time that people might be able to come for a review session as well. And it might be Thursday evening or sometime on Friday, something like that. I don't like to put it off till the day before the test. That's not giving you enough time to learn from and study from them. But anyway, we'll have some review opportunities coming up. And one of the things I'll give you is the test from last time I taught the class, so you can see what kind of questions I do ask on them. So that'll be part of your review material. Anyway, I'll turn you loose for the day. Have a good afternoon, and I'm going to head out to work and do the experiment for this